Welcome to Brain Vision.
Okay, so problem 750, we have a 1,500 kilogram rocket that is launched from initial upwards, that is to be launched with an initial upward speed of 50 meters per second right here at the end of this ramp. And we're going to start it at rest of a ramp that's 53 degrees above the horizontal, and at the bottom it turns up, and then that's what makes the 50 meters per second when it turns up. Okay, so the engines provide a constant forward thrust of 2,000 newtons, and friction from ramp surface is constant 500 newtons. And we're asked how far from the base of the ramp should the rocket start, as measured along the surface of the ramp. So that's this distance d. I put y here because we'll need that as well. Okay, so let's write our conservation of energy formula. So we're going to have K1 plus U1, and that's going to be G. And then we have that plus the work due to the rockets, plus the work due to friction. And that's going to be equal to U1 plus U2 plus K2. There's some immediately here we can cross off. So it starts off with 0 kinetic energy because it starts at 0. And then we're saying that it just instantly turns up at the end here. So we can write that the U2 gravitational potential is going to be 0, and there's no other potential energy there. There's only kinetic energy of it moving up. Okay, so we can write down what each of these pieces are. So we can write down what U1G is. So then that's going to be equal to the mass times gravity times the height. So that's 1,500 times G times Y. Now we can write down an equation for what Y is in terms of D. So D times the sine of 53 degrees. Sorry for overlapping that a bit. Equals Y. So we can substitute that in at the end. Okay, so work due to rockets is going to be equal to the 2,000 newtons times the distance traveled, so that's d. And because those are collinear and they're and the force is in the same direction that it's propagating, that's going to be a positive sign there. So positive. Work due to friction. The force is going to be a different value, but it's opposite to the propagation of motion. So then that's going to be negative, and it's the same distance. So it's going to be minus 500 d, and then K2, we're practically given. So that's 1/2 times the 1,500 times the 50 meters per second squared. Okay, so then plugging this all together, we have the 1,500 G sine of 53 degrees. And then we have plus 2,000 minus 500 is plus 1,500 D. And then we have that is equal to the 1/2 1,500 50 squared. Okay, so that's going to be our equation for finding D. Okay, and I actually forgot what to put in the D there before the sine of 53. So then we can cross off the 1,500, that's in each term. And then I can pull out the D. So then that is G sine of 53 plus 1. And then that's equal to 1/2. 50 squared is 2,500. And then solving for what G sine theta, sine of the 53 degrees is, you get 8.83 equals to 1250. And then that means that we get D is equal to 1 for 1.5 meters.